Okay, in this video we take up where we left off in the last video on solving problems that involve physics strings. And in that problem I worked this problem, which had two masses, M2 and M1, connected by a string and pulled by a second string with a tension of 10 newtons, where the mass of this block was 5 kilograms and the mass of the second block was 3 kilograms. And because it was a physics string that didn't stretch, and I therefore knew that the accelerations, velocity, and displacement of these two objects were the same, I was able to just treat this as a single body and work this problem, and it saved me a lot of algebra. Now I'm going to work the problem treating each mass separately, writing Newton's laws, and then doing the algebra, and at the end I'll show that I get exactly the same answer as far as the question, what is the acceleration of the blocks? But if you wanted to know something about this string here, the tension in this string, then you would have to go about this other step. So usually what's done is if you're looking at a bridge or something else, you'll do the whole thing, find its acceleration, velocity, what have you, and then work backwards with the individual free body diagrams of the pieces to find out about stuff concerning forces inside the structure or object. So that's what's normally done. You use the trick first, find A, and then you can plug it into the equations. But I'm going to do it the longhand this time. I'm going to actually use the individual parts and do a bunch of algebra to simplify. So first thing first, I have two masses, M2 and M1. Remember, we're treating the strings as having no mass. So for each mass, you need a free body diagram. Also, something I left out in the last one because I didn't care about that part of the problem. This thing obviously must be residing on some sort of surface here. I know I left that out, but otherwise gravity would make it fall down. That's because I was only caring about this direction of the problem. So there really is a surface, and I've been assuming throughout that this surface is frictionless. Okay, so for the first body, M2, it would have a weight, W2, and I left out in the previous video there would have to be a normal force from the surface. So I had in mind floating, if you would. And then there would be some tension. I'm going to call that tension T1. That tension is the force applied by the rope because of M1. So it's M1 applying the force on M2. The string just acts as a way to provide that force. All right? It's not the string applying the force because the string has no mass. It's really this object applying a force on M2, and therefore M2 must apply a force on M1 in the opposite direction. So when I draw its free body diagram, it has a tension force, and it will be exactly the same value. Notice this is exactly the fact through the third law about the string. The string's tension right here is T1, whoops, and that T1 on the string is in this direction, so therefore M2 pulls on the string this direction, then the string pulls on M2 in the opposite direction. And likewise, the tension here, we said for physics string is the same as on the other end, so in that case, this string is being pulled this way by M1, so it's pulling M1 in the opposite direction, and that's shown on my free body diagram. Here we have weight W1, we have force N1. This free body diagram has that coordinate system, and likewise the coordinate system over here. You may think, well, that's kind of a waste of time, but we'll see later on that sometimes these coordinates may look different or be rotated as we go from one object to another in order to connect their motions. Now, let's read the free body diagrams. We only really care about the x direction in our problem, so sum of the forces in x is equal, in this case, that's M2. And for this free body diagram, sum of the forces in x is M1 AX. Notice that the mass here needs the subscript to match which object you're talking about's free body diagram. Now there are also y equations, but we don't care about them right in this case. We're looking for acceleration along x. If I look at this, the w and the n there along the y, T1 is the only force along the x. Over here, I've missed a force in drawing my free body diagram. I had this rope here pulling on that, so I need to make sure I got that. M2AX. Over for this forces, I have T in the plus minus T1 is M1AX. Now here's something neat to note. The easiest way to work a set of equations involving two objects like this is to add them. And the reason is the third law. Here you'll have a positive T1. That's the force being applied by M1 on M2. Over here you'll have minus T1 by the third law. If the force M1 applies on M2 is T1, then the force applied by M2 on M1 is the same magnitude, T1, but in the opposite direction, so it'll have a minus sign. If we add, call this equation 1 and this equation 2 together, we get T1 plus T minus T1, where I've added the left-hand side of both equations. And on the other side, I got M2AX plus M1AX. Notice the T1's cancel. I get T is equal, I can factor out an AX, M2 plus M1 AX. And this is exactly the same equation that I had previously for my single block. And what that shows you is this. Considering this to be the body that I'm talking about, like I did in the previous video, this was the total mass, M1 plus M2. So that's what went in Newton's second law, mass times acceleration. But the only force outside the blue box is T, this force here. That force is inside. So what comes out is T. Had I broken it up and done the algebra, I get exactly the same equation. This is the reason it's important to remember when you speak of Newton's second law. It is the sum of the external forces. And by external, I mean those forces that pull on the body outside the free body diagram, okay, at the edge of the body, these forces. It's not the forces between the atoms and parts on the inside. And the inside includes a string. So by shrewdly choosing the free body that you're going to consider, what object you're going to consider the free body diagram of, you can eliminate several lines of algebra. You can eliminate all of this work and been able to jump right to here at the bottom. Tension is equal to the sum of the masses times AX. And of course, if you put in these numbers, T over M1 plus M2, you'll get the same thing we did before, 10 newtons over 8 kilograms, 1.25 meters per second squared. Now, I could, like I said, could have jumped to this line right here, right off the bat like I did in the other video, and I could have found AX. Once I find AX, I could take that and plug it into here, and because I would know the mass, M2 is 3 kilograms, I could find the tension in this rope. So maybe the second question that somebody asks you is, what's the tension in the rope? Using 1, we have for T1 is equal to 3 kilograms times 1.25 meters per second squared, and that's equal to 3.75 newtons. Now you might say, but what if I didn't use this formula? What if I chose to take this and plug it in over here? It's got to work out the same. It has to work out the same. It doesn't matter which equation you put in. So you can take this, plug it in here, and if you get the same answer for T1, that's when you put 1.25 in for here, when you put in 10 for here, if you get the same T1 that you did for this equation, that checks your work. If you don't get the same answer, you've done something wrong. All right? Any type of string problem is done this way. This is just a standard method for attacking physics problems involving physics strings. Alright, we'll talk to you on the next set of videos.